guys, welcome to the let's see. This is the second session of day 6, and we're looking at WAN encapsulation and configuring serial interfaces when my PowerPoint went kaput on me. I was doing some demos, and I was trying to kind of keep it going and get my computer to reboot, and it rebooted, and it gave me I guess the Windows 8 install disk was still in it, and it gave me a Windows installation setup window. So I said, this is a pretty good time to take a break. Fortunately, for all of us, the computer, I kicked the disk out, and it hasn't chosen to start up from there in a while. But kicked the disk out, we're booted, we're working again, so we can dive right back into the slideshow and pick up where we left off. And that was just looking at basic configuration of serial interfaces. So this is just showing router A and B, configuring the serial interface, and again, we talked about that bandwidth statement. So if you do the show controllers command, this has been, like I said, something that they've quizzed us on forever. And I feel bad because I don't know how many network engineers actually use the command, but they've asked you to be able to use this to identify which side of a serial connection is the DCE or DTE end. Here we can see that router B has the DTE end, so the clock rate command would go on the other side. Feels silly even teaching you that. I don't know that you'll use it at any time in reality, but it's something you should probably be ready to see on the test, possibly. Looking at the HDLC protocol, this is our default encapsulation method. This is an alternative to Ethernet. This is what's used across serial links. It's a very simple header because there's not a lot going on with these frames. You send them in one side, it comes out the other side. What they're showing you here is an HDLC frame, and then they're showing you a Cisco HDLC frame. And the Cisco frame has got a protocol field. Protocol field indicates what we're carrying at layer 3. And they say that Cisco's HDLC is proprietary, but I believe everyone's HDLC is proprietary. So vendor, if it's within the same vendor, you can use HDLC. When you go to a different vendor, you'd use a different protocol. We can validate the encapsulation both by doing a show interface command and reading the encapsulation line. And additionally, you can do a show run interface 00, as we saw earlier, to validate that encapsulation. The point-to-point protocol, as I mentioned earlier, it's standards-based, so different vendors can do it. If I need to go Cisco to Juniper, I could go ahead and use PPP or to any other vendor, and it also is going to support authentication. So PPP has a layered architecture. There's basically two sublayers, what they call the network control layer, which faces the network layer, or layer 3, and there's the data link layer, which interfaces with the physical layer. So there's a lower layer and an upper layer. The link control layer, which talks down here, and the network control protocol that talks above. PPP involves both. Looking at the encapsulation on a router, really straightforward. We just say encap PPP, and as I showed with Wireshark, you'll actually see PPP frames going across the wire instead of HDLC. Still not a lot to look at there. Here they're just showing you both sides having an encap set to PPP is going to bring the connection up. You can validate it here with encapsulation PPP. And if you wanted to put PAP or CHAP on top of it, you can. So PPP can support authentication. There's two mechanisms, PAP and CHAP. PAP is our password authentication protocol, which sends the passwords in clear text. So the way that you configure this can be pretty confusing. So tune in here and watch closely. What you do is you create user accounts in the local user database. What's the local user database? It's your running config. So for example, I could come over here and say config t, username, and I put the host name of the opposing router. So I'm on R9, I would say username R6, and I would say password Cisco. Let's not get fancy. I'll just say password Cisco. And then what you do on R6 is the reverse. You go into global config, and I say username, and I put the other router's host name. Well, the other router that I want to connect to, if we look at our topology diagram, R6 is connecting to R9, right? So I would come in here and I'd say username R9. Again, that needs to be the host name of the other device. and then we say password, and the password needs to match. And it was Cisco, just like this. I'm going to double check, make sure that looks good, and we should be in good shape. So once you set the correct username and password on both sides, they're in the local user database. You just have to tell the protocol to use authentication. Now, you could use PAP or CHAP. CHAP is the other style of authentication, and what makes this a little bit different is that it does what's called challenge handshake. It's a challenge handshake authentication protocol. Now, this is used in PPP, which is a WAN technology. So if you're in class and you're looking at this going, man, this is a lot of data to absorb, I'm going to be selective about what I learn. This WAN stuff isn't that important. Unfortunately, it is. They're going to hit you with it on the exam. And then later in life, say you go into the security path and you're in one of my CCNP security classes and we're talking about 802.1x, and I go, you know how CHAP works? And you'd go, wait, what? That's that thing I selectively forgot from CCNA. Well, this is a topic that's going to come up later in life if you go down the security path. It would be common practice for someone in security to know the differences between PAP and CHAP. PAP sends your username and password in clear text across the wire. What CHAP is going to do, as I mentioned before, is a challenge handshake. So what the heck is a challenge handshake? Basically, one side is going to challenge the other. That's what we see here. So the headquarters router is sending a challenge. Now you're wondering, what exactly is a challenge? Well, it could look like this. There we go. It's just a funny looking string of characters. When you get that funny looking string of characters, you take it and you take your password and you run these through a hashing algorithm. What a hashing algorithm does is it takes variable length input, meaning it takes any data that you provide it and it generates a fixed length output. Variable length input creates fixed length output. In other words, you're going to create a digest, and you send that digest across the wire. Now, hashing is a one-way function, meaning if you know the data, if you know the input, you can run it through the algorithm and recreate the output or the digest. But you can't take the digest and reverse it. Is everybody on board with that? For instance, if you go download Linux Mint, which is a nice, crisp, clean, free operating system, and you download that ISO, maybe it's 2 gigabytes. And if they provide an MD5 hash, this is a 128-bit hashing algorithm, the digest for this file, the checksum that MD5 creates, digest, checksum, hash, those are all words for what it puts out, will be 32 characters. Now, if I was to take Ryan.txt, which is a text file, and if you open it up, all it says inside of it is Ryan, and I was to run this through MD5, it would create a 32-character checksum. There's no way that you could ever take that checksum and reproduce Ryan.txt, the same way you couldn't take this 32 characters and recreate a 2 gig ISO. But if you have that 2 gig ISO and you know the hashing algorithm, you can recreate that checksum at any point. So the principle that I'm trying to drive home here is that your password is not being encrypted. Okay? Encryption is two-way function. You encrypt it and then you decrypt it and you get the original data back. What challenge response is you send the challenge to the other side. They take the challenge and their password, run it through MD5, for instance, and they come up with a digest. You send the response, which is the digest, to the other side. Well, what he did locally was he took the exact same challenge that he sent you, and he took your password, which is stored, he ran it through a hashing algorithm, and he created a digest. If the digest that headquarters created matches the digest that you send, then you must really be that user. Does that make sense? Thumbs up if it does, thumbs down if it's a little bit foggy. Hopefully everybody feels good. Very, very cool. You'll see chat being used all over the place. There's an MS chat, there's EAP that implements MS-CHAP. There's CHAP over PPP like we see today. For your understanding and testing purposes, here's what you really need to walk away with. Understand that CHAP sends hash values, not passwords, across the link. And then the far end that you're authenticating to actually recreates that. And what we're really comparing here, our Coke versus Pepsi, is PAP versus CHAP. This is going to send your passwords in the clear. This sends a digest of the challenge plus your password. Do we feel okay? Probably not going to implement it anytime soon, but if somebody says MS-CHAP to you, you know that that's not digital certificates. It's usernames and passwords, and specifically with a digest. So the configuration of PAP or CHAP, we need to enable PPP. Well, we set this up previously in the demo as PPP on both sides. Now we just need to enable authentication. We're going to do authentication using the opposing host name. So this is my R6, this is my R9. I create a user account of R9 over here. I create a user account of R6 over here. I make the passwords the same, and I turn on PPP authentication. So we have everything done. Here we are on router A, and we say username router B, which is this guy's host name, with a password of Cisco123. Put an IP address on the serial interface, say encapsulation PPP. The only thing that we don't have is PPP authentication, PAP or CHAP. And then you just do that to both sides. So let's take a look at doing this with PAP real quick. And we've got EAP, CHAP, PAP, MS-CHAP, and MS-CHAP version 2. We're just going to do PAP. And if we come over to R9, see that it already went down because we've got a mismatch. One side wants authentication, the other side's not giving it. Now we set the authentication, and it should come up, but a quicker way to make it happen is shut the interface and then no shut the interface. Should try to resynchronize, should try to authenticate. And let's see if we get a statement for line protocol change state to up. That all looks good. Show IP interface 000. Serial interface is up, line protocol is down. Sometimes this happens. This has happened in past classes where it looked to be configured right on both sides and it was just being fussy. So the interface change state to up, we're looking for line protocol change state to up. You can do a debug PPP authentication. So PPP, authorization required. Maybe the other side isn't sending it. We can come over here and do debug PPP authentication. Same thing, authorization required. cov-t, int 000, shut, no shut. See if that's enough to make it happen. All right, let's try one more thing. We'll go int 000, and we'll say PPP authentication CHAP. And it came up right away. So when moving it from PAP to CHAP, it worked just fine. Let's validate that. Do show IP interface brief. And it should have worked the first time. It just didn't. Don't know why. We can try it one more time, PPP authentication. And I say just try using the simple method. Interfaces should come down. See where this leaves us. Okay, cool. So this time we're up and up. I turned it from PAP to CHAP and it worked. I turned it from CHAP to PAP and it's still working. Show interface 000. We can see here that we've got encapsulation of PAP. I think we can do a show PPP. It's not going to give us any good details. But we should still have our debug going on over here. And we see that everything's working. So show interface 000. Line protocol is up and up. And I can ping across 10.10.69.9. That's me. 69.6 is the other guy. And you see we can communicate across here just fine. All right. So additionally, other things that you might have seen, here's CHAP. These are the actual responses being sent back and forth. There's our challenge. There's our response. And then once the session is up, we should start seeing CDP data being exchanged. Those are my pings. And then we'll just see CDP periodically. And you'll see PPP has this link control protocol that we saw on the slide. Those are just the messages going back and forth between the two hosts to make sure that they still have link. So did I do PPP for authentication? I did, but if you didn't see it, let's go back and take a look. We'll bring up our device, and let's say show run interface 000. And notice that it's PPP authentication PAP. The first time I did this, it didn't work. And then when I changed to CHAP, it worked, and I moved it back to PAP, and it worked the second time. So if you set things up and they don't work, double check your configuration, look at it really, really close, try shutting and no shutting interfaces. And I always remove the authentication and see if it works, and I re-add it. And that's not real scientific, but it tends to do the trick, as you just saw. So PPP authentication. Oh, it needs to be on the interface. Int 000, PPP, authentication, CHAP. Same thing here. Conf T, PPP, authentication. Come on. Oh, not on the serial interface. And then we can shut, we can no shut. And we should see it come back up again. So it's up. It's just suppressing some of the logging messages. I turned on logging, and it might have got too chatty. Yeah, console monitoring's on. But again, we can see from show run int 000 that we're now using CHAP, and it's fine. Any other questions, Eric? Doing good. Okay, great. So that's moral of the story. HDLC is your default encapsulation, but it's not vendor neutral. So possible test question might be something like, you need to hook a Cisco router to a non-Cisco router using serial connectivity. What encapsulation method should you use? It would be PPP. Now, if we want to perform authentication and we're worried about security, the better solution would be CHAP because it doesn't send our credentials across the wire. That's a recap of everything we just learned. Here we're just doing a show interface 000. You can see the encapsulation is PPP. You can do a debug PPP authentication. You typically shouldn't have to. My routers that I'm in are being emulated in Dynamips, so it's pretty good for messing around with, but it's not exactly what you're going to see in real hardware sometimes. What you should have seen was a bit more chatter in the debugs, but this is pretty straightforward. You can look at this and see whether you've got a success or a failure. And just after your success, you'll get a status message typically that says the line protocol changed state to up. The interface changing state to up is no big deal. That's layer 1, and that means there's a wire plugged in. That doesn't mean a lot. This can be the trickier part at layer 2, and that means we've got our encapsulation and authentication correct on both sides. So as far as troubleshooting, we can use show controllers to verify we've got the DCE or DTE end, and we want to make sure that DCE has got the clock rate command. With a show interface, we could look at the interface output and make sure our encapsulation is correct. HDLC is the default where PPP's got authentication. If we're having problems with authentication, we can do a debug PPP authentication and actually see the success or failure. And if it's succeeding, our interfaces should be up and up. And then we can just follow that up with a ping, which would prove we have a functional link. All right. Another common topology that you could have if you didn't have a dedicated line would be a virtual circuit, which means we have a shared connection across the WAN circuit. So what we're going to do is between here and here, we'll have frame relay. Everything here is going to be Ethernet, and it's probably going to be Ethernet over 10 gigabit per second or greater fiber. So we just use frame relay at the edges, and then they've got rules to perform frame relay switching and get your packet over here, and then it goes frame relay out the other side. When you call the service provider and you say, I want a connection that goes from point A to point B, they'll set up what's called a PVC, a permanent virtual circuit. And they'll assign you a DELC, which stands for Data Layer Connection Identifier. The data layer connection identifier here is 100, and this is the ID that goes on your frames that you send into the link. Now, what they're showing here is that this is our headquarters site, and it has 2 connections. One connection is going to get you to one remote office. The other connection would get you to the other remote office. So your DELCs are local. Whenever I send something in with a 400, maybe it says to route it over there. Anything that comes in with the 100 gets routed over here. So each of your offices that you need to communicate with have different DELCs. You guys okay with that? The way that they represented that in our slide is here. They say these offices are connected, DELC 100 and DELC 200. Over here, they call this DELC 400 and DELC 500. This is just an ID, and it's locally significant. This is what you think you're getting, is that connection between the 2 offices. What you're really getting is what you see here. Wired connections into these frame relay switches, which are moving your packets through their provider network. Now, the crazy thing about DELCs, see if they're going to show that. Yep, they're going to show it coming up. So I won't get into that just yet. Just want to make sure I had a slide for it. I'll tell you now, it's the opposite of ARP. What do I mean by that? Well, if these 2 routers were connected by Ethernet, I would send a layer 2 header that had a destination MAC address that corresponds to this guy's MAC address. And my layer 3 header is going to have a destination IP that corresponds to his IP. Does that all make sense? I'd look at my ARP cache and I'd see the far side's MAC address. And that MAC address goes with that IP address. Everybody with me? I haven't told you anything new yet. I'm just confirming that we all know what we learned before. This is where frame relay gets super weird. I'm telling you now, and I'm going to tell you again. DELC is locally significant. So when you go to the service provider, if this is Tampa, Tampa has a connection to Atlanta, and the Tampa to Atlanta DELC is 100 in Tampa. And Atlanta, their DELC to get to Tampa is 200. But what's super weird is if you think about your layer 2, you're sending it to DELC 100. But the destination IP is over here. So in other words, it's your local DELC is going to be mapped to the remote IP. looks the opposite of what we saw with Ethernet and MAC addresses. And over here, if router B wants to send a message to Tampa, he sends it at a layer 2 perspective to Del C200, which looks weird because it's local. But when the service provider gets something with Del C200, they've got frame relay map statements. It's going to get that over here. So once again, it's your local Del C to remote IP. Cool? And that's just a preview. I'm going to tell you this in a slide with better examples, but at least it won't be the first time you've heard it because it's confusing. If you got it right now, you're doing great. If you're halfway there, that's perfect because we're going to talk about it again. Frame relay supports multiple topologies. It could be point-to-point. It could be a partial mesh. It could be hub and spoke. It could be full mesh. Hub and spoke is where you have everyone connect into headquarters. And then if you want to get from, let's say, router A to router B, I'd have to send my packets to headquarters and then go right back out that interface. Everybody okay with hub and spoke? Full mesh means everyone's connected to everybody. It's ideal, but it's expensive. And partial mesh has some fault tolerance because if one of our hubs goes down, we've got backups. If you were to use a hub and spoke topology, it could result in some reachability issues. Frame relay is considered a non-broadcast multi-access environment. What does that mean? Well, it's not a broadcast environment like Ethernet. However, if we look at what's happening here, everyone's got these Del Cs that bring you to headquarters. But if you look at all the spoke sites, they're on a common subnet. So you've got 10.1.12, 10.1.13, 10.1.14, 10.1.1.1. Notice that everybody is part of the same network. If you send an update through RIP, which you probably wouldn't do, or EIGRP, which is more likely, there's a rule called split horizon that comes into play. What does split horizon do? Can anybody tell me? If you haven't read about split horizon before, basically it says if somebody gives you routing information in one interface, so in this case on serial 0 on the router at headquarters, if routing information comes in this interface, split horizon says don't send it back out the same interface because the guy over there already knows about it. Well, the problem here is that this is a serial interface, and we've got all these other neighbors out there on a similar IP block. But each of those neighbors is just connecting to us in terms of the routing updates, because the way that the frame relay connections are laid out, it's like 3 individual circuits that all terminate on headquarters. Well, headquarters says if a routing update comes in serial 0, don't send it back out serial 0. So for example, if we're running EIGRP across this environment, and we'll call these routers A, B, and C for clarity purposes, and this guy headquarters, if router A sends a route advertisement, he says 10.3.1.0 is located over here. Our EIGRP update comes in, and what split horizon says is don't send that back out serial 0. Do you see the problem? We can't tell router B and C about how to get to 10.3.1.0, and we need to. So what we do is we disable split horizon on that interface. Does that make sense? Normally, we wouldn't want to do this. But because of this topology, this is what we could call point to multipoint. We've got one interface talking to multiple destinations. You may want to receive an update in that interface and send it back out. So we would disable split horizon. Other things that you could do to simplify this include the creation of sub-interfaces. This is a problem to NBMA. Non-broadcast multi-access means everybody's on a common subnet, but you don't broadcast the way that you normally do. Everybody doesn't have connections to everyone else. So in that scenario, we could create several point-to-point networks. What you do is you take your physical interface and you chop it into sub-interfaces. See how they did that here with a decimal? Serial 000.1 .2, and .3. Each of these have separate IP address blocks. So here's an IP address block on a /30. Here's a second one. And here's a third one. In other words, what we did was we carved out our serial interface into 3 virtual sub-interfaces. And each sub-interface is used for a point-to-point link. Goes like that, and like that. In the previous example, if we go back and look, everybody was on one big network. See the /24s and all those routers? But they can't really communicate like it's a broadcast. So this is point to multipoint. This is point to point using sub-interfaces. Each of the sub-interfaces on my headquarters router is in a different subnet. Do you guys see that? He's .1, .5, and .9 all at the same time. And each sub-interface only talks to one other router. Each sub-interface is associated with a separate frame relay permanent virtual circuit. So it's like we've got 3 separate wires here coming into 3 separate interfaces, which gets rid of any of the rules in routing that we had to worry about breaking. So this gets us out of any of the headaches that you might experience with routing protocols. Is there an advantage to using sub-interfaces versus disabling split horizon? Yeah, you could associate different policies with each physical interface. There's something later that you'll learn about called class maps and policy maps for doing modular QoS CLI, and you associate those with physical interfaces. You can do QoS and rate limiting on an interface by interface basis, so it gives you more granular control. Additionally, it takes some of the headache out of our routing protocols. So for customers that I have seen that are using frame relay still, what they tend to do are point-to-point sub-interfaces because it makes it idiot-proof. You can forget about split horizon. You can forget about EIGRP's got something called next hop self that's activated as well. We don't have to think about that. In terms of OSPF, it simplifies things as well. Remember, OSPF in a broadcast environment, it's going to elect a DR. Well, in this topology, we want to make sure headquarters is the DR, and we want to make sure that the guys who aren't headquarters don't become the DR. So you go into each interface and you say IP OSPF, and I'd say like priority 10 on headquarters, and I'd say priority 0 on the branches, so that the branches don't try to become the designated router, because that would be suboptimal. So you have to go in and kind of whip your routing protocols around to work in an NBMA environment. If you jump over here that's the signaling. We're already on it. This was our multipoint, and our routing protocols have to be manipulated to get them to work right here. Over here, the routing protocols are simpler. So yeah, this is definitely preferred. So your local management interface is going to give you the ability to communicate with upstream equipment. There's 3 different LMI standards. This is signaling that's sent across your serial interfaces. And there's 3 standards. You've got the Cisco standard, you've got one called ANSI, and one called Q933. This is going way back in history. I'm going to use this in a bit. But basically, when I get a frame relay circuit provisioned, I get an email from the service provider, like Verizon or Sprint or whoever you're using, and they're going to tell you your DELSI, and they'll tell you your LMI. And basically, these are just configuration parameters that we set on the serial interface so that it knows how to talk to the far end. We just need to make it match on both sides. Not a lot to say outside of that. The frame relay address mapping can be discovered using LMI. So this is where it gets a little bit more exciting. Frame relay address mapping is basically like ARP, but for serial links. What we need to do is map together the local DELSI with the far side IP address. So this DELSI might be 200 over here. Doesn't matter because DELSI is locally significant. What I need to see in my router is that if I want to reach 10.1.1.1, I need to send the frame on DELSI 500. And if I want to reach 10.1.2.1, maybe I've got a separate DELSI that'll get me there. That could be DELSI 300, for example. So I'd send a frame to 300 to reach that other router. Each one of these has got its own, what they call PVC, or permanent virtual circuit. So far, so good? So this is LMI itself is not that exciting, but using inverse ARP to map our local DELC to the far side makes it a little bit easier. If we didn't have this, we could create a static mapping from the CLI. I could say this DELC goes with that far side IP. So the way that it works is your router comes up, brings up the serial interface, and he sends something called a status inquiry. This frame relay switch is going to respond to us with active. There's active, inactive, and deleted. Inactive and deleted are bad. Active is good. He says, you are DELC 100. I go, fantastic. I go, by the way, I'm 172.168.5.5. On the far end, he's doing a status inquiry, and he says, you're DELC 400. And he goes, fantastic. I'm 172.168.5.7. The ultimate result of this is you're going to learn that DELC 100 maps to 172.168.5.7. Does that make sense? And this guy's learning that DELC 400 is what he uses to get to 5.5. This is what our frame relay mapping would look like when we're done. If I want to get to 5.7, use DELC 100. Over here, that should actually be a 400. He'd say if I want to get to 5, and that should be a .5. He's saying if I wanted to get to the other side, I would use this. Use DELC 400 to get to 5.5. So you could configure a static frame relay map if your provider doesn't support inverse ARP, which they would. If you want to control broadcast traffic across a PVC, you could do that as well. That allows your routing protocols to work across this. Or if you want to have different frame relay encapsulations. So all that we do is set up the serial interface just as we did before, but we say NCAP frame relay. And then there's the other side. It says NCAP frame relay. And then with your sub interfaces, any question on point-to-point versus multi-point, this is where the headquarters broke out sub interfaces, and each sub interface connected us to a different site, and I had a /30 to connect to each of these independently. With multi-point, you can use a single IP block for everyone, but multi-point can save address space because it all happens in a single subnet. It's used for partial mesh and full mesh topologies, but you've got to tweak your routing protocols to behave appropriately for the environment. So what they're doing here is showing you how to create point-to-point sub interfaces on the headquarters router. Serial interface, the physical interface itself, gets no IP address, but we do set the encapsulation. Then we break out serial interfaces. And they said 0/0/0 dot, and what sometimes they'll do here is use the DELCs. So DELC 110 and DELC 120 is what they used as the sub-interface ID. You don't have to do that, but it makes life a little bit easier. Then we say, is it point-to-point or point-to-multi-point? Point-to-point's the easiest to work with, and that's what we've got happening here. On the branches, we say encapsulation frame relay. You could do serial interfaces just so you're ready for the future. And here they are defining the DELC. Nothing special. And there's your other router, branch 2. NCAP frame relay, and then they're doing everything on a sub interface. You don't really have to do sub interfaces at the branch offices, but if you did want to set up more if you wanted to set up more frame relay point-to-point links in the future, you wouldn't have to change your existing configuration. This is basically future-proof because for future interfaces or future connectivity, I would just create more sub-interfaces. What topology do most corporations use? It would be point-to-point sub-interfaces like this. Just because it simplifies all of our routing protocols, which tend to be the most challenging to have to manipulate. In a multi-point frame relay environment, this would be less common. We're putting everything, and they're just showing off doing a sub-interface here, but they're creating a sub-interface, and instead of being point-to-point, they do multi-point, which means that you're going to go out here, and you're going to reach multiple destinations that are all in the common subnet. And then what we do to make this work is we create static frame relay maps. We say frame relay map. To get to this IP address, use this DELC. To get to that IP, use that DELC. And if you get a broadcast or multicast message, send it through both DELCs. So in other words, if you send a message out to 224.0.0.5 to do that OSPF hello, it would carry that exact message over both links. We could discover branch 1 and branch 2. They'll send messages back and we'll form our adjacencies. So the broadcast keywords needed for your routing protocols to work. And again, what you see below are just static mappings of DELC to IP address. And what I said wasn't real intuitive is this could be DELC 333 and this could be DELC 444. When I'm setting up the far end, I use my local DELC to the far side IP. Local DELC, far side IP. I think that's the most confusing part about it. And here, they're just setting up multi-point frame relay on the branch router. And all they're doing is mapping 10.1.1.1 to DELC 110. Local DELC, far side IP. Same thing on branch 2. He's got a DELC. This doesn't really match up. But see how he's using 210? 210 would be the local DELC here. And the far side IP address, 10.1.1.1. And again, just doing a show interface, we want to see that interfaces are up and up. We want to see the encapsulation is frame relay. Additionally, we haven't seen this before. We can verify that the LMI type is Cisco. Just needs to match whatever your provider is using. And if you do a show frame relay LMI, we can see stat counters for status inquiries and status messages. We see our status inquiries sent and status messages received. So basically, we've got a good communication path between us and the service provider. We don't see a bunch of errors here. We're actually getting responses. And if you do a show frame relay PVC, this is going to show us our permanent virtual circuits. So there's our DELC, and there's the interface that we use to talk to it. And we see a status of active, which is good. Show frame relay map, this is basically like looking at your ARP cache. It's showing us the remote IP address and the DELC that goes with it, whether we learned it statically or dynamically, and whether or not it supports broadcast. All right, so that wraps up frame relay. In reality, I don't know that you're going to run out and implement frame relay anytime soon, but the old guys that wrote this course just left it in there, so we had to talk about it. What you'll more than likely, I'd imagine everybody in the room is going to use at one point or the other, is going to be a virtual private network. VPNs are classified as site-to-site, which is connecting one network to another, or remote access. This connects a user to the network, where this connects one office to another office. That would be a good way to think about it, or one subnet to another. When we look at VPNs, a lot of times it's just to connect a branch to a headquarters or headquarters to a data center. They're virtual because we're leveraging a public network and we're building a private network across it. It's private because we're using encryption, such as AES, to keep our data confidential. The benefits here are cost savings, widely scalable, compatible. It's a standard, so it works with everything. It's very secure, and we can set it up quickly and easily. If you look at getting frame relay provisioned, it might take you several weeks. Mark says, would site-to-site VPN also be called L to L? Absolutely. Sometimes they call it LAN to LAN or business to business. Good questions. Looking at VPNs, you've got two good remote access solutions. One is using the AnyConnect client. This is software that you download from Cisco that you would install into Windows, Linux, or OS X. They've got clients for all three. And if you didn't want to use a client, you could use clientless VPN, and that's where you just simply use your browser and you type HTTPS webvpncompany.com and a web VPN portal comes up. IPsec is the protocol that most people think of when you hear VPN. Times are changing though. If we go back a slide, Most of your remote access connections today leverage SSL, not because it's better, but because it uses TCP 443, which everybody understands. In other words, if I've got a user at some hotel and they want to go through the hotel firewall, this firewall is going to allow TCP 443. If they didn't, nobody could shop online, nobody could do online banking, no one could get into anything securely. So everyone allows TCP 443, which is what SSL uses. When you look at site-to-site VPNs, those are going to be IPsec based. When you look at older remote access VPNs, those were IPsec based. When we do IPsec, it's basically doing this. It takes, let me get a whiteboard. You've got an end user, maybe on their laptop, that wants to use an application like Remote Desktop. So we take RDP, which has a TCP header and has an IP header with private addressing, right? RFC 1918 addressing. And when you build a VPN connection, you might go over the wireless at the hotel, which gets you to their router, which is going to do NAT, which gets you to the internet, which is going to get you to the corporate ASA. All right. When we launch our VPN connection, we launch the AnyConnect client, and it's going to build a connection to the ASA using UDP 500. This is where we negotiate all of the parameters for setting up a tunnel, and this is where we authenticate. Once you authenticate and your profile gets pushed down for how you're supposed to connect, all of this traffic is now going to be encapsulated inside of an ESP header, and then ESP goes over IP. So in other words, the packets that you send to this NAT gateway are ESP packets riding on top of an IP header. ESP, or encapsulating security payload, is what you have at layer 4. And this can be problematic. Can anybody think of why we might run into some problems here? TCP has port numbers, UDP has port numbers, ESP, while it's layer 4, doesn't have port numbers. It's got a value called a security parameter index. If you're at the Holiday Inn, is that router doing NAT or is it doing PAT? We should have learned the difference in ICND 1. If we're at a conference center, if we're in a hotel, if we're on an airplane, if we're on a cruise ship, if we're at a Kinko's, it is doing port address translation. It overloads lots of users onto a single IP address. What's the problem here? ESP has no PAT. Well, we have no port numbers, so we can't PAT. So our packets get thrown away. This causes some headaches. So they created a Band-Aid for this called NAT-T, NAT Traversal, that says wedge a UDP packet here. So put a UDP packet in front of that ESP packet. So when it comes up to the gateway, he has a way to do port address translation. So that fixes our problem, but it adds additional overhead. And the ASA is listening over here on UDP port 4500. Well, this can be problematic. Did the firewall admin at that hotel or at that airport know to let through UDP 4500? Maybe. Did he allow through TCP 443? Absolutely. So SSL VPN using TCP 443 should work 100% of the time. IPsec-based VPNs, which are just as secure and actually a little bit more efficient, are using UDP 4500. That will work most of the time. If you can give me a solution that works 100% of the time, that's what I want to put my users on. And nothing truly works 100% of the time, right? It's technology. But realistically, TCP 443 is going to be let through. UDP 4500 may not, ESP isn't going to work. So for remote access, SSL tends to be a cleaner, more reliable solution, where IPsec is what we will use for site-to-site connections. So it acts, they say at the network layer, kind of, because it's encapsulating the original IP header and a new layer 4 header, and then you put a new layer 3 header on the outside, at least if you're in tunnel mode. It's a framework, which means it's standards-based, and as new algorithms are created, it can go ahead and utilize them. Its goal is to provide confidentiality, which is privacy. It gets this through encryption. It provides data integrity. We want to know that our data wasn't altered in transit. So AES as an encryption algorithm makes our data private. MD5 does hashing, and it can prove integrity. You can have the source of the information include a key when it creates a hash. They call this hashed message authentication code, or HMAC. So basically, we get 2 for 1. If somebody sends us encrypted data, we're going to decrypt it, and we're going to run a hash against it. That hash is going to include a key, and if the hash with the key work, it means we're getting this data from an authenticated source. Anti-replay protection just means you can't capture encrypted data off the network and then send it again later. It would know that that data wasn't part of an existing session. All right, so that was IPsec, and that brings us to GRE. GRE is probably one of my favorite concepts of this, at least of this chapter. GRE is silly packet stunts. When someone tells you that you can't do something, you go, yes, I can, and you set up a GRE interface. A lot of the things that we talk about in the VPN course are based upon GRE. GRE is the shoe edge that we can make any protocol on Earth work over an IP network. So if you have legacy protocols like AppleTalk or DECnet, and you wanted a DECnet server in Maine to talk to a DECnet server at a factory in Atlanta, well, if they're going to communicate, they can't communicate over IP. They're DECnet, it's different. So you would have to get a leased line, and you'd have to get routers that could do DECnet and set up a dedicated network that's totally isolated from IP. What GRE allows you to do is have a DECnet interface, take in DECnet traffic, and when it gets here, put it inside of GRE. GRE is just a big storage container that allows you to carry traffic from one point to another over an IP network. It's just a box that anything can go in. We're going to cover GRE. We've got 2 days left. So what we're going to do is cover GRE tomorrow in a good amount of detail. And then once we've covered GRE, we'll take a look at network management. So got some good stuff ahead of us. The WAN chapter is over. I guess I enjoy that stuff from a nostalgia point of view, but I know it's not real exciting to learn about. 10 gigs exciting, 40 gigs exciting, VSS and Nexuses and VPCs and virtual distributed switches and Nexus 1000Vs and virtual load balancers and virtual firewalls and cloud. That stuff's exciting. Show me, frame relay, makes me want to go to sleep. But we're through that part now. That's the legacy stuff that you had to know for the test. Everything from this point forwards is going to be highly, highly relative. You'll probably use GRE in the future if you need to do any cool packet stunts or do anything really tricky. I could do like a layer 2 MPLS VPN equivalent using GRE in like 2 minutes with no provisioning. So you'll learn to love GRE, and tomorrow we'll also get into network management. We'll continue that on Thursday. So if you guys have any questions at all or anything that you'd like to discuss, stick around and feel free to ask questions. If you don't, that's a wrap for today, and I hope you have a great evening. Thanks so much for joining me.